In the previous session, we considered the goodness of fit of our model. In this session, we'll have a look at the quality of our measurement. Specifically, we will consider two indicators of quality: average variance extracted and construct reliability. What does it mean that a measure has a good quality? In survey research, one sign of quality is internal consistency of items. To assess quality, we would look at the consistency of answers between different questions within a questionnaire that are supposed to measure the same constructs. Reliable measurement would generate high consistency in response to questions. Reliability is estimated using three indicators: Cronbach alpha, composite reliability, and average variance extracted. Cronbach alpha is calculated in SPSS, and in this tutorial we will consider composite reliability and average variance extracted, both of which have been proposed by Forner and Larker in 1981. Both are associated with very scary formulas. Here is average variance extracted, and here's construct reliability, but I'll show you in this tutorial how those formulas are easily broken down and calculated using an Excel file. Let's for the moment go back to our AMOS output and begin to judge reliability of our measurement. Please open your AMOS 3 construct model and then go to text output. And then using the menu on the left here, go to a page called Estimates. You begin by looking at the top table here to see whether job satisfaction or motivational performance are really related to the indicator variables. Those relationships are significant if here in the column P you see stars. P becomes a number where it starts being insignificant relationship. So if there are stars here or numbers that are below 0.05, you are in the clear. As you see, all our relationships are significant. That one here comes from the fact that we had set one of the relationships at 1 at some point, but no matter. We are good so far, all relationships significant. Next, we looked at the next table, which is called standardized regression weights. These are in fact factor loadings like the ones in factor analysis, but for some reason creators of AMOS labeled them as regression weights. You look at this column here to judge the strength of a relationship between satisfaction and JS4, for example. The figure you're looking for is at least 0.5, but better still 0.7 and higher. As you see, we have nothing here below 0.5. There's 1.6, but everything else seems good. You next have to use these values to calculate composite reliability and average variance extracted. I just copy the AMOS output into my Excel file. So I go into estimates and I pick this bit and I select it, and then I copy it and I straightforwardly paste it into my Excel file like so. Paste. See, the number we are looking for, the number we need are these estimates, and I have prepared one earlier, so I copied and pasted the estimates that correspond with particular observed variables. For some reason AMOS has reversed the sequence, but it doesn't matter. Here are the estimates, and then I calculated all the elements of the formula. Just to make things easier to see, I am going to hide stuff that we don't need for a moment. So let's do that. So let's begin with average variance extracted. To calculate it, we need the estimates and we need to square them. So this cell here 0.52 comes about from multiplying cell D4 0.724 times 0.724, and I've repeated the process. See D5 squared, D6 squared, and D7 squared for all the observed variables. I then, in the next step, added these all up. Here I have a sum 2.06. Now, average variance extracted is an average because we divide the sum by the number of indicators, in this case by 4. And we have average variance extracted for our first construct. And I have used this spreadsheet to calculate it for construct motivation and then construct performance. What we are hoping for is a value above 0.5, and you will see that all three have met this criterion. Next, let me unhide things. Let's move on to construct reliability. To calculate that value, you need one further element of the equation, delta. Delta comes about from taking away from 1 the squared estimate. So here we have a value of 0.48, which comes about from taking 0.52 from 1. And I have repeated the process for all 4 observed variables. You see the results of deltas here. And I sum those, added them all up in here. So here is delta for each estimate, and here is the sum of delta. I have also added all the loadings together, those ones, added them all up here. They came to 2.87, and that then squared that number. So you will see 8.23 comes about from multiplying the cell I7 times I7. And these are all the numbers you need to calculate this magic 0.81. How this comes about? We have a denominator which comes from adding sum of loading squared and sum of delta. This, in our case, equals 1017. I'm dividing sum of loading squared by this denominator, coming to an estimate 0.81. I have repeated the process for all 3 of our constructs, and the results are 0.85 and 0.91. Importantly, all 3 are above the magic figure of 0.7. Here we are. We have AVE and CR above the recommended value, meaning we have a reliable measurement model. So how good is our model? We have looked at the significance of estimates. We have looked at the AVE and CR, and we have analyzed those values and decided that they are all acceptable and above the recommended values. The conclusion that is, our measurement model is acceptable. Let me just recap what this tutorial was about. In this tutorial, we looked at reliability of our model, and we used 2 indicators, average variance extracted and construct reliability, to determine how good our model is. We have calculated the formulas based on estimates from AMOS and decided that our model is acceptable. Reliability of measurement is a necessary step for estimating structural model. Now that we established good reliability, we move on to the next step, structural model, and in our next session we'll begin to estimate hypotheses that link our concepts into a theoretical model. See you then. Bye.